Well, during this symposium, it's one constant question: what the breeders really need? And now we are going to have a talk with one mathematician that was converted into physiology and molecular breeding and many other fields, that he has been working close with breeders, and he's going to present, well, he's Greg Rebetzke from Cicero, Australia, and he's going to present a talk about effective delivery of phenomics in a commercial breeding. It's more a question of what and when, and not how.
It's the really big, it's hard to spell.
This.
Thank you, everybody. It's great to be here talking about work coming out of my group, and just want to acknowledge the very talented and diverse team, physiologists, remote sensors, and commercial breeders who I work with. I also just want to thank the organisers, and particularly acknowledge Matthew Reynolds, just showing his abilities as a sensory phenotyper in the market with me on Sunday. So thank you, Matthew. Yeah. And that's Graham. So I guess I work very much at the interface between some of the omics which underlie the basic research, including phenomics, the application of that technology and delivery into commercial breeding. And it's been stylised in this image, which is a funnel, which just, I guess, demonstrates the activity and also the funding, which sits across basic research and delivery into commercial breeding and ultimately to growers. We talk about this basic research and applied research as pre-breeding, and the success of that pre-breeding and its delivery very much reflects the connectedness between the basic research, the applied research, and how that's integrated into total packages. And unfortunately, much of the work that we do see published in high-impact journals doesn't make it to breeding programs because of that disconnect. And the reason that disconnect occurs is because the challenge for us as researchers is to better understand what are the questions being asked for by the breeders. What is trait value? Prioritising traits relative to each other, and what are the traits relevant to the target environments? In selecting, if it's a glasshouse study, does it need validation? Is that complex trait, or that phenotype, is it quick, cheap and reliable? Is it heritable? Is it consistent over backgrounds? And then finally, how does that gene or trait fit into my target farming system? So I work on wheat, and wheat in Australia is very narrow genetically. Effectively, we start with a crossing program, and we move through glasshouse to the population development, and then the bottleneck in terms of the genetic diversity that makes it to the breeding programs, to the advanced stages of testing, is the nursery. And nurseries in Australia are not particularly large because the traits that we're targeting are very, very focused on adaptation and quality, but also the nurseries are not particularly, the replication is small, and so there's less confidence in being able to select those lines with elite potential to make it to the first stages of replicated testing, stage 1 and stage 2, and ultimately to the advanced stages of testing. In looking at the capacity for phenomic selection, I guess we've made some decisions and given some consideration that the greatest benefit in terms of delivery in phenomic selection is through physiological enrichment, through traits that we're targeting, particularly at the nursery stage. We have the capacity to massively increase our population size, but also increase selection intensity, because we'll have the capacity to phenotype and identify traits using the capacity for repeated sampling, increasing heritability to increase confidence, but while also working in those large populations, increasing selection intensity, so we still manage the same numbers of lines, making it through to those more expensive stages of advanced testing. So for us, nurseries become the real bang for buck. We can bring in greater diversity from CIMMYT, from other places around the world, and we can accommodate these larger populations and screen them or enrich them physiologically or genetically meaningfully. So these are the sorts of nurseries that we tend to deal with in Australia, from these hill plots here to nursery rows. And by the F4 stage, much of the added genetic variance, that part of the genetic variance that responds to selection, is among families, so we can screen diversity, but also we can use phenotypic enrichment to look for those traits that we're targeting, traits that are often lost because breeders throw a lot of material out for disease or quality, and so we're able to retain important alleles, important traits linked to adaptation, using high-throughput phenotyping. The example I want to give where we're investigating this is around biomass, and in much of the world, particularly in the northern latitudes of Europe, harvest index, or yield, is a function of harvest index and biomass, and we are starting to run out of variation. We're maximising the potential for further genetic gains through harvest index. Grain yield is increasing in this work from John Folks, but we can see that harvest index is plateauing off. And this is not restricted only to the UK, but we're seeing evidence of this across the world. But we are seeing evidence of increase in radiation use efficiency and the capacity to select for biomass. And there's some very interesting germplasm around in Australia and overseas which reflect this capacity to better utilise light more efficiently. Erect canopies, ligulous germplasm with the potential for improved radiation use efficiency. In Australia, biomass is a key driver of adaptation in our water-limited environments. So we're, again, very interested in biomass, not only in those high yield potential environments in the UK and Europe, but also our water-limited environments in Australia. But biomass is very difficult to measure. It's very complex genetically. It's also very expensive. Measuring biomass using traditional methods of cutting, we estimate, or we do this actually in our ground truthing, 10 people takes 32 hours, 320 hours in the field to screen around 2,000 rows. But with the capacity of LIDAR, using platforms such as the Phenotyping, we have the capacity to increase our screening for biomass with one person, taking 2 hours to undertake screening of approximately 20,000 rows. So huge potential to screen much larger populations and to do this in a way that is cheap but also safe and so we've got a small experiment where we looked at confirming the capacity for using LIDAR to screen or select for biomass in individual or spaced rows. The experiment was conducted in the Managed Environment Facility, Yanko, 60 genotypes, 2 environments. It was a row column design. These were irrigated trials, and biomass and LIDAR sampling occurred at mid-tillering in single row and plot. And these were undertaken under our controlled environments, which are field environments, which are supported for by a grower body, the GRDC, and located across 3 sites throughout the Australian wheat belt, Narrabri, Yanko and Merredin. And these sites give the capacity for assessing up to 4,000 large plots under well-managed conditions where we can control water very well. This is an image taken, or some data taken from the LIDAR, indicating what the plots look like. We had wide rows here and narrow rows, and cuts were taken. LIDAR was run over the plots before the cuts, and then again after the cuts, shown here. How did we go? Well, for a simple trait like canopy height, the LIDAR did a very, very good job in predicting plant height on a single row, but also across plant height in a full plot. The different circles represent whether the rows were taken from narrow rows or wide rows. When we look at the capacity for LIDAR-based biomass prediction for single row and conventional row spacing, single row on the x-axis and the actual biomass here on the y-axis, the LIDAR did a very, very good job of predicting actual plant biomass, both at narrow rows, to a less extent wide rows, but still a reasonable correlation. When we correct for area, so we're moving away from individual row biomass and look at row biomass on an area basis, we can see that the wide rows were very much light limited. And so it may explain in part why the correlation with biomass and the LIDAR was quite poor. But certainly at narrow rows, very typical of conditions in Australian wheat breeding assessment, but also growers, the association between the LIDAR index for biomass and plant biomass itself was very strong. When we bring all this data together, we can actually then understand the capacity to use LIDAR in predicting biomass using the power of correlated genetic gain. So on an entry mean basis, biomass, actual biomass, had a reasonable heritability, but it was nowhere near as high as that for LIDAR. And this is LIDAR being run just once. The additive genetic correlation for biomass and LIDAR was quite high, but because the heritability for biomass itself was high, I guess the relative response to selection for biomass using LIDAR was not as efficient as biomass itself. However, we move away from the capacity for replicating biomass cuts in the field. Remember, they're very expensive and slow. We move to a single row situation. The biomass for heritability is quite poor relative to that of LIDAR. And from that, we can then understand that the relative gain on using LIDAR-based index for biomass was about 23% better or higher than that for biomass itself. So, and as we heard yesterday, there's also the capacity to use repeated measures to increase at least that sampling component of heritability to improve our confidence. The other important feature with this, of course, is the markedly reduced cost in the use of the LIDAR and the non-destructive phenotyping, and the capacity then to retain seed for validation or testing in larger plots. So where do I see the value in LIDAR? As we've demonstrated in our own group and Graham in the sorghum group, is really around pre-adapting. Can we use some of these new tools to effectively enrich for alleles as we're moving through the breeding pipeline for traits which are going to be important in pre-adapting performance in our target environments. Once we fix those alleles, in this case, the example before, biomass, really it's then about, okay, what other alleles are out there? Those other alleles which are probably less heritable and do require the costly job of multi-environment testing. But I'll try this one comment too. Just because it's cheap and available off the shelf doesn't necessarily mean it's going to be useful. I guess I'm a little frustrated with some of the technology-driven science that I'm seeing in literature. And one example of this is NDVI. I guess in our hands, NDVI does not perform very well in predicting biomass. And it works very, very well in early stages, in estimating in ground cover. And it also works very, very well as Matthew and others have demonstrated in looking at dynamic trends or changes in stagering. But once canopies are complete, saturation occurs, NDVI is a pretty much useless predictor of biomass. My last couple of slides really is extending the capacity for phenomics beyond selection to addressing subclinical spatial variation. So here's a couple of images from a field study. You can see very, very uniform plots. But when we actually look at aerial imaging through canopy temperature or through multispec, we start to see that there are some real issues with these field trials, requiring us as breeders to actually go and look and understand what is contributing this variability. Is it disease? Is it subsoil constraints like soil acidity? But also giving us some understanding and some capacity to better model what that spatial variability looks like when we move to the next stages of analysing our data. So just some take-home messages. I guess I just really wanted to emphasise, in my opinion, it's really hard to replace selection for yield in multiple replicated field experiments, but physiological enrichment using phenomics does give us the capacity in early generations to bring in more diversity and pre-adapt our populations. And my last slide here is, good biological understanding is leading to some really useful field-based tools, permitting high throughput phenotyping and selection. But again, the technology should not define the research question and use. It really is our understanding of the biology and the needs we require, that really should be driving where that research and the technology development should occur. So just to finish up, just acknowledging some really clever and talented people I work with, and also the link to the commercial breeding programs. And honestly, no matter what you hear in this whole conference, it's all about this slide here. So thank you.
Okay, we have time for a couple of questions. If not, can I do one question?
Oh, absolutely, Hannah.
How good is selecting with your LIDAR in the second and the third generation? Because still biomass, as you say, is a pretty complex. The heritabilities are not that high. So do you think that is a good strategy, start to selecting that early, or it would be better to start a little bit like an F4 or...
Well, certainly F4, 1.5 or almost 3/4 of the added genetic variance is among families, and so that component of the variation you see, at the F4, 3/4 of the total added genetic variance is among families, and so that component of what you see and is heritable actually responds to selection. So F4 is a good time to do it. In terms of using LIDAR later, absolutely, it's going to be very useful. Graham gave some examples about the use of phenomics in, I think, corrected genotypes. But for me, and I think this is really important, in a real breeding program, diversity kills us, or lack of diversity kills us, and it's at that stage when you're doing most of your selection that you set the bar. The threshold in terms of the additive genetic variance and the mean occurs at that point. So if you can screen more reliably and bring in greater diversity, you're enriching and you also maintain the capacity for greater genetic gain, not only in this cycle, but in subsequent cycles. So for me, it's about using these tools much, much earlier, but reliably and confidently in being able to screen amongst that massive diversity.
Great.
This is not going to be a hard Kiwi question, is it?
Just thank you for the talk again and emphasizing on the principles specifically about NDVI. Anyway, but I was wondering if, why is it that the correlations for height are not very high? The correlations for LIDAR and plant height are not, very high, like over 70%. I expected a bit more than that.
I think they're pretty good. They're phenotippic correlations. I think they're not too bad, given the wide range in the population. So.
Yeah, I meant the earlier stage. You talked about the plots and then the rows.
Yep.
I think the rows were improving this, but the plots were lower. Is that correct, or I got the wrong message?
I think you may have got the wrong message. I guess this slide really demonstrates for a more repeatable trait like height, how the rows do predict the full plant heights quite well. So.
Okay, thank you very much.
Thank you. Thank you. Good question.